Hey everyone. So in this video, I like to talk about even and odd functions. So we've been talking about function transformations for a little while now, and one example of a transformation is a reflection. For example, if I take my function, if I take a function and I negate its input, what this does is it reflects my function's graph horizontally over the vertical axis, right? So here, if I imagine sort of my vertical axis here, maybe I'll label it y, this negation of the input amounts to reflecting the graph of that function over that y-axis. Whereas if we negate the function itself, or we negate the output of the function, what this does is it reflects our graph vertically. And so here this takes our function and it reflects it over, for example, maybe an x-axis, a vertical reflection. So sometimes a function looks the same after it's been reflected. And so it can be useful to take advantage of this symmetry, and so I'd like to give this symmetry some language or a name. And so here I've got three different functions. F of x is equal to the absolute value of x, g of x is equal to negative x squared plus 4, and then h of x is equal to this function we haven't talked about, and we're not going to talk about in this quarter, but you'll see in a later pre-calculus class. 3 times cosine of x plus 1. And so here are three graphs, and we can see that each of these three graphs, if I imagine reflecting their graph across this vertical axis, because each of these graphs look the same to the left and to the right of this vertical axis, such a horizontal reflection is going to really keep the graph looking the same. Right? And so such functions that look the same after a horizontal reflection are called even functions. And so maybe to give this a little bit more meaning, a function is even if I take some x value and I look at the negative of that x value, and we examine the outputs corresponding to these two x values, we get the same result. Right? So here, if I look at an input and it's negative and we get the same result every time, we call such a function an even function. And that's really the same as saying that the function is symmetric, looks the same or mirrored across this vertical axis. And so here, we can kind of write this in function notation. A function is even if I take f of negative x, and it's really the same thing as f of positive x. And so one thing I want to emphasize is that a function being even doesn't necessarily mean there's an even exponent involved, right? So of our three examples, 2 of them didn't even involve an even power, right? So one of them was the absolute value of x, that was an even function, it was symmetric about our y-axis. There's no even power there. And then the other even function we had was this cosine function, and again there was no even power there either. So here, something I want to emphasize is that even functions don't necessarily need to involve an even exponent. And actually there are also many examples of functions with even exponents that are not even. They're not even functions. And so here's one such example. If f of x is equal to x minus 3, and then I square that, well, x minus 3 squared, that's like our x squared function shifted to the right 3 units, right? It's a transformation of our x squared function by replacing the input with x take away 3, and that amounts to a shift right 3 units. And if I reflect this graph over the vertical axis, if I look at f of negative x, what we get here is this graph. And because when we negate this input and we reflect over this horizontal, or sorry, this vertical axis, we do a horizontal reflection here, and we don't get the same graph, we're saying that this function f of x is equal to x minus 3 all squared. That's not an even function. And so, sometimes it's beneficial to be able to verify an idea without necessarily having to graph it out. And so here I want to show you how we can verify that a function is even or not algebraically. So this f of x function, it's not even, but if we simplify, we get out x squared minus 6x plus 9. And so if I replace my input x with negative x, in other words, here I have, I'm squaring my input negative x. I have minus 6 times negative x, and I add on 9 at the end. Right, so I take essentially my f of x function and I replace its input with negative x. Right, what we get out is, well, if I square negative x, right, I have negative x times negative x, that's the same as positive x squared. I have negative 6 times negative x, that's the same as positive 6x. And then I have this 9 added on at the end of the day. This is really the same as f of negative x. That's what f of negative x is. And we can see that these are not the same. Right, f of x and f of negative x, these are not the same. And so we've algebraically shown that f of x is not the same as f of negative x. We don't get the same outputs for taking or plugging in an input and it's negative. So this function f is not an example of an even function. Right, an even function would have the same result because we did not get the same result here. This is not an even function. So I have 3 more functions here and their graphs. And although these functions aren't even functions, right, if I reflect these functions horizontally over that vertical axis, we don't get the same graph. There is some symmetry here that I want to talk about. Now if I look at this f of x function is equal to 1 over x, if I take this function and I reflect it horizontally, right, I don't get the same result. I don't get the same graph. But then if I take this function and again reflect it vertically, I do both the reflections, now the graph looks the same as what we started with. And actually that's the case for all of these 3 functions here, is that if I reflect over both the horizontal axis and the vertical axis, I get the same graph, or at least the same looking graph. You can also think of this as taking my graph and rotating it 180 degrees around the origin. So these are 2 different ways to look at the same thing, but I want to focus on reflections here for a moment. So here, if I have a function and I reflect over both the horizontal axis and the vertical axis and I obtain the same graph, we call this kind of function an odd function. And so just like how we did this for even functions, we wrote that in function notation. To write this in function notation, if I take my function and I reflect it horizontally and vertically, we get the same result. That's what we call an odd function. And actually, usually, it's not quite written in this way. Usually it's more convenient for us, or more useful to us, to write it as f of negative x is the same as negative f of x. So this is the way it's usually more beneficial for us algebraically. But these 2 ideas are really the same thing. So if some function satisfies this property here, we call it an odd function. And so pictorially, if I take some value x out here, and I look at its negative, and we examine what the function outputs at these values, they're going to be the same quantity, just negatives of each other. That's really what we're saying is the case for an odd function. And this is going to be the case for all of the input values of our odd function. And so here, let's go ahead and verify that this function g of x is an odd function. Let's do this algebraically. So g of x is equal to 2x take away x cubed. So let's verify that g of x is equal to 2x take away x cubed is an odd function. So let's do this algebraically. So what that means is that if I take my g function and I negate its input, what we're expecting out is a negative of this g of x function. And so what happens when we negate this input? We replace that input with negative x. Well, we get 2 times negative x minus negative x to the third power. And so 2 times negative x, well, that's negative 2x. And then here, negative x to the third power. Let me write it like this. This is negative x times negative x times negative x. So if I count all these negatives up, I get a negative, I get a positive, and then a negative out at the end of the day. And then there's 3 sets of x's being multiplied. This is negative x cubed. So here I have minus. This doesn't look all that different, but it truly is negative x cubed. And so here, applying that negative of that, or with that subtraction sign, gives me negative 2x plus x cubed. And how does this differ from our original g of x function? Well, it almost looks like g of x. It's just off by a negative sign, right? If I factor out that negative from both of these terms, and I'll do this in red, we get 2x minus x cubed left behind. And this is our g of x function. Right? This is g of x. And so really, this is the same. At the end of the day, it's really negative g of x. So we're saying that g of negative x is the same as a negative g of x. This is exactly what it means for our function to be an odd function. And so the last point I'd like to make is that a function can be neither even nor odd. Right, so we saw one example earlier. We said that, for the example f of x is equal to x take away 3 squared. We saw that that function was not even. It's also not odd. Right, if I take my function f of x is equal to x take away 3 squared, and we saw that when we reflected it over the vertical axis, we reflected it horizontally, we didn't end up with the same function. And we also see that if we reflect this new function, this blue function, vertically afterwards, we still don't end up with the same graph. And so here, the fact that this graph was not identical to our original graph told us that the function was not even, and the fact that when we apply both reflections and we don't get the same graph, that tells us that our function is not odd. And so here, if I look at this function g of x is equal to x cubed plus 1, if I use this as another example of something that's neither even nor odd, here's the graph of the function g of x is equal to x cubed plus 1. And if I take this function and I rotate it, or maybe I'll say I'll reflect it horizontally and I'll reflect it vertically, we don't get the same result. These two graphs aren't the same. And so here this function is not an odd function. Although it's x cubed plus 1, there's that odd power, it's not an odd function. And it's not an even function as well, because we saw that when we reflected it horizontally, we didn't get the same graph.